Hi, Assalamualaikum. Welcome back to my channel Physics for 5 SSM. Today we continue chapter 7 Quantum Physics on topic 7.3 Einstein Photoelectric Equation. In this video, I will discuss two learning standards. The first one, explain production of photoelectric current in photocell circuit. The second one, describe application of photoelectric effect. Figure 7.15 shows a photocell circuit. So you can see it consists of cathode, which is a curved pieces of metal, anode, and also glass tube, which is vacuum tube. The cathode is connected to negative terminal of the battery. Anode is connected to positive terminal battery, and there is a milliammeter to measure current. So from this circuit, we want to explain how the current is produced in this circuit and detected by milliammeter. Figure 7.15 shows a photocell circuit consisting of a glass vacuum tube. The semi-cylindrical cathode is coated with light-sensitive metal and connected to negative potential. The anode is a metal rod fixed at the axis of the semi-cylindrical cathode and connected to the positive potential. When the photocell is illuminated by light, the production of photoelectric current is produced in the circuit. If we look at here, why the cathode is curved and the anode is placed at the center or the fixed axis of the semi-cylindrical cathode is so that the photoelectron is focused and received by anode. Let's look at the table below here. The table shows two examples of common photocell, caesium and lithium. As we know, different type of material will have different threshold frequency and also different value of work function. Let's look at for caesium. Work function W equals to 2.14 eV. Threshold frequency FO equals to 5.16 times 10 to the power 14 Hz. Maximum wavelength to produce photoelectric current lambda equals to 579 nanometer. So this one can be calculated by using lambda equals to C divided by FO, or we call it threshold wavelength. For lithium, you can see the work function W equals to 2.50 eV. Threshold frequency FO equals to 6.03 times 10 to the power 14 Hz. Maximum wavelength to produce photoelectric current lambda equals to 496 nanometer. So you can see for lithium, it requires higher frequency as compared to caesium in order for photoelectric effect to occur. On the whole, the higher the work function, the shorter the maximum wavelength required. So you can see here, the higher the work function, the shorter the maximum wavelength required to produce photoelectric current. Once the photoelectric effect occurs, means photoelectron will be attracted to anode and produce current. As the light intensity increases, the photoelectric current in the photocell circuit also increases. We have discussed earlier that intensity increases means number of photons that reach the surface of cathode also increases. In other words, number of photoelectrons emitted also increases. As a result, in the circuit, if number of photoelectrons emitted increases, the magnitude of current flow in the circuit also increases. As a conclusion, we can say that as intensity increases, the photocell current or photoelectric current also increases. I hope you still remember the photoelectric effect that we discussed before. Frequency of light much larger or equals to FO, or threshold frequency. And then kinetic energy maximum does not depend on intensity of light, but depends on frequency of light. That one, high intensity of light means increase in the number of photoelectrons emitted or increase in the photoelectric current in the circuit. You can refer to activity 7.9 to observe how photoelectric current is produced in photocell coated with cesium through computer animations. You can use this link to observe the animation video. So based on the simulation, explain how photoelectric current is produced in photocell coated with cesium. When light at certain frequency f is equal to threshold frequency of metal FO, electron will be emitted at the surface of metal. The potential difference across anode and cathode causes photoelectrons to be attracted to anode, thus current flow in the circuit. Let's look at application of photoelectric effect. The use of photocell and also solar cell. The first one is LED lamps along the road which are powered by solar cell are energy efficient and environmentally friendly. In daylight, the photoelectric effect of solar cell enables electrical energy to be stored in the battery. At night, the LED lamps will light up with the power from the battery. So you know this one is solar cell. The no-complex solar power plant located in the Sahara Desert is the world's largest concentrated solar power plant. The station is expected to be completed in 2020 and is capable of producing 580 megawatt capacity for use by 1 million residents. So this is the solar cell. Light detectors at the automatic doors use infrared beam and photocells as switches. When the light path is disturbed, photoelectric current in the photocell circuit will be disconnected and the door will remain open. Automatic door. The image sensor is a main component in high-resolution camera. This component is used to convert light into electrical signal which can be processed to form digital images. This one is operation of ISS, International Space Station, depends on the source of electrical energy generated from solar panels. The ISS has 16 wings of solar panels and each wing which measures 35 meter times 12 meter has 33,000 solar cells. These panels are capable of generating 84 to 120 kilowatt of electricity. So it means the solar cell or this component of photocell are greatly application by using photoelectric effect. Let's look at formative practice 7.3. Number 1, state Einstein photoelectric equation. We have E equals to W plus K maximum. For K maximum equals to H bracket F minus F1. State the meaning of work function, threshold frequency, the relationship between work function and threshold frequency. Work function is minimum energy required for electron to be emitted from metal surface. Threshold frequency is minimum frequency of light for electron to be emitted from metal surface. Work function is directly proportional to threshold frequency or can be represented by this formula W equals to HFO, the product of Planck constant and threshold frequency. Number 2, A. Sketch a graph to show relationship between maximum kinetic energy of photoelectrons and frequency of lights shown on the metal. Okay, this is the graph, K maximum against frequency. So you can see the graph shows increases linearly graph. Intercept at one value that we call it threshold frequency. B. What are physical quantities represented by gradient and intercept of the graph sketched in 2A? So from here, the gradient is equals to K maximum divided by F minus FO. If we put one point here, at F, the value of K maximum, we just put as K max. So the gradient of this line is equals to K maximum divided by F minus FO. From the formula of, or the equation, from the equation of photoelectric by Einstein, so we have K maximum equals to H bracket F minus FO. From here we get H equals to K maximum divided by F minus FO. Thus, from here we can see the gradient of this graph actually equals to Planck constant. Intercept at the f-axis is known as threshold frequency, and we extend the line to intercept at Kmax axis. What we get here is the value of work function. Because from here, if we calculate the gradient of the graph for this part, we'll get W divided by FO equals to H. Because same gradient just now is the Planck constant, means gradient here is also Planck constant. Okay, so the value of here W divided by FO equals to H. So we get back again the formula for work function, W equals to HFO. Okay, thus the value intercept at Kmax axis actually is work function. Okay, so remember for this graph, K maximum against frequency, the gradient is equals to Planck constant. Intercept at x-axis or f-axis is threshold frequency, and intercept at K maximum axis or y-axis is work function W. Number 3, when a metal with work function 4.32 times 10 to the power of negative 19 joule is shone on by a violet light, given the wavelength, what is maximum kinetic energy of an emitted photoelectron given the Planck constant, the speed of light in vacuum c? From the formula of Einstein photoelectric, from the formula of Einstein photoelectric equation, K maximum equals to energy of photon minus work function. The work function is given here. So HF minus W. There's no F given, so we need to calculate for F, which is equals to C divided by lambda. So from here we get HC divided lambda minus W. Okay, substitute the value of HC and lambda. The lambda in meter already, as I need, minus the work function. So we get K maximum equals to 6.53 times 10 to the power of negative 20 joule. Okay, that's all my video today on chapter 7, quantum physics. You can search for more information on this topic to understand better. Thank you for watching. Bye.